So let's talk about ResNets. So if you had to pick like a worry-free off-the-shelf network right now, I would probably recommend that you go and pick a ResNet or a ResNeXt. And there's a reason why they worked significantly better. And again, the initial motivation was a bit strange about gradients not making it through the entire stack and whatever. Here's what's really going on. So suppose I have a deep network, right? And then I decide I'll go and make it even deeper, right? So we can make it deeper by just adding another layer. And by adding another layer, I get a slightly different function class, right? If I add another layer, I get a slightly different function class still. And of course, I have more parameters, so I can do more interesting and diverse and powerful things. But basically, my function classes get bigger, get more powerful, but they're also different. So if you look at the picture on the left, you can see a set of function classes, each of which is a little bit bigger than the previous one, so thus a little bit more powerful. But they're all a little bit different. Now, let's assume that the truth is out there, right? This blue star is the truth. And I want to approximate that truth. And as you can see, is as you start adding layers and layers, you're going to get closer and closer to that blue star. And once you've reached about that third network from the dark black to the darker gray, you can get kind of closest to that blue star. And then, as you start increasing the function class further, you start moving away again. And that's really undesirable. And there's no guarantee that you might not eventually also come back again, right? After all, you don't know exactly what happens if you add another layer, because you don't know where that blue star is. And this is awkward because this makes it very hard to reason in some meaningful engineering way over how many layers should I pick? How complex should my function class be? Right? Now, on the other hand, if you look at the picture on the right, things are much nicer. And typically, if you open any paper on statistical learning theory, they pretty much all assume that you have a nested function class. So if you take any non-parametric statistics class here in the stats department, I'm willing to bet you that almost all cases, unless they come with specific warnings that it's not the case, assume that you have the situation on the right. Unfortunately, with deep networks, you have the situation on the left. So how can we make it a little bit closer to the one on the right? On the right-hand side, the function class still get larger. As a matter of fact, I drew that right plot by just taking the picture on the left and making it smaller, right? And just centering it. So it's the same powerful, power of function classes, just that they're nested. So as I move from one to the other, they become more powerful, more expressive. I can reach a larger function class. And so now, as I keep on adding, I move closer to my blue star. They're not necessarily convex, but that's just what it is. So I want to have the situation on the right. How do I get there? And this was the ingenious idea by Hare et al. 2015. Namely, rather than parameterizing around the function f of x equals 0, being the simplest function, and that's basically if all the weights are 0, I parameterize around the function f of x equals x. Because if all the weight parameters and everything is 0, if I add the input to the output, then I get the identity function as the simplest function. And that's quite brilliant. So it's like a Taylor expansion for neural networks, right? At least that's a similar flavor. So now as you increase your parameters, you're starting to deviate from the identity function. So now I don't have to learn the identity function that does nothing to my data anymore. So it's essentially assuming a different inductive bias. It also means that as I add another layer, the identity function still goes through, and it will still, leave the outputs of the previous layers unchanged, just that I could now do additional things to my output. Of course, it's not exactly how it works, that I didn't exactly implement those nested function classes, but I did something that was pretty close to that. And so this is what a ResNet block looks like in detail. So you have a convolution, a batch norm. So this is the batch norm that we talked about before. Rectified linear unit, another convolution, another batch norm. And to that, you then add the input. Or you run a one-by-one convolution on the input and you add that to the output. But at the very least, you're making it fairly easy for the network not to change things if not changing things is the best thing to do. Okay? And so here's the code. Code is fairly straightforward, right? This is now skipping a lot of details of setting the variables. This is just the forward function. And what I get is y is batch norm 1 of convolution 1 of x. And also then I apply a ReLU, and then I apply another batch norm 2 of conv 2 of y. And then if I'm in the situation where I have the path on the right here, then I just apply conv 3 to x and I add the two results together. Of course, I need to pick my convolutions and everything in such a way that the dimensionalities still match up, but we already saw how to do that for inception. Now we can use it for batch norms and basically to get a basic ReLU block. Any questions here? Because that's really the heart of how a ResNet works. Okay. Now you might think that this is straightforward. Well, people tried all those different flavors of batch norms. They try and where to place the batch norm, where they place the addition. So in some papers they use the batch norm after the addition. In some cases they used had the addition at the very end. In some cases they permuted the order of ReLU, conv, and batch norm, and so they tried out all three different permutations. So the sequence between the blocks is the same, but the order is changed, right? And yeah, there are papers for all of those, and for some combinations, on some days, in some settings, some of those things work better. Now this sounds thoroughly unsatisfactory, but this is unfortunately the seedy underbelly of deep learning training. But in some cases you just have to try out things. And then at some point somebody does this, figures out, okay, this is a good architecture, and then people pretty much stick with it. Okay, so here's the ResNet module. So this looks, quite familiar to what we saw before, just that now it's using, ResNet blocks rather than inception blocks. So you might have, one of those blocks which downsamples, so stride 2. And then you have a couple of the other ResNet blocks. And that works well. And here's the entire network in its full glory. So that's ResNet 18. Goes up all the way to ResNet 150, so that's 150 layers. And the bottom looks, kind of very scarily similar to whatever we saw before. Wide convolution, batch norm, pooling. And then you have a whole bunch of ResNet blocks of different size. And you train it. And we will train that next week, not today. What this gets you to is this thing up here. This is now ResNet 152, and it's pretty much state of the art. It's slower, but it's much more accurate. It's actually smaller in terms of footprint than the inception network that we saw before. That would have been the orange circle to the right. I'm going to conclude with something that you think can go even further, namely ResNeXt. And that has a neat idea in it, and yeah, Camming here was one of the co-authors on that. And essentially it relies on the following observation. If this is our ResNet block, right, so we have a 1 by 1, then maybe a 3 by 3, then we have a 1 by 1. So we have 64 channels, and then we have 256 channels, right? Or, you know, some choice like this. So you might ask yourself, well, is this a really good idea? And it turns out that you may be able to do better by just partitioning things such that my inter-channel interactions now happen only by groups of, let's say, 4. So what I'm doing is I'm basically taking the network on the left and slicing it up into 16, or in this case, you know, more networks that just have 4 channels, or, you know, some larger number of channels each. And then in the end, I stack everything together. And so this, of course, means, if we look at that, so initially we have, you know, height times width times input times output channel, you know, parameters. And the computation is, you know, of course, you know, output height and width times, you know, the corresponding height and width of the kernel plus input times output channel. We can break things up by, you know, 1 by 3s and 1 by 5s and 5 by 1s. That's what we saw before for inception. Or we can break up the channels. And so if I break it up into B groups, then I have Ci over B groups for the input, C output over B groups for the output times B, because I now have B groups. So in other words, I get a reduction by a factor of 1 over B. And as a result, I can use more dimensions, and I'm in good shape. And that's really all that there is to it. So this is very easy to add to any code that you might have. Basically what you do is you just set in the 2D convolution the variable groups to, you know, whatever number of groups that you want. That's it. Now if you compare ResNet and ResNeXt, the computational budget is very, very close, right? Number of parameters is, you know, within like a few % of each other. Number of flops is very close, but it works a little bit better. And with that, I'm going to conclude because, yeah, we're out of time. So, any questions? Okay. So next week, we're going to cover different networks, some more in code. The other thing is, there's this thing called an exam, right? Right? So, a couple of things for